All right, so on the family theme, I'm going to start off with the family photo album for the LMR. It's been a truly rewarding journey for me. I've learned a ton, and I've really had a blast, continue to have a blast. So we have the PIs up above. We have staff, students, postdocs in the middle, more students and postdocs at the bottom playing various different roles. I can't introduce everybody to you. Most of them are in the room, so hopefully I'll get a chance to talk to them. I'd also like to say a public thank you to the sponsors. A couple people in particular. Dave Verardo at NSF, you could, as much as anybody else, is the founder for Paleoclimate data assimilation that got this whole field started. Our program officers at NOAA, Bill Murray to start off with, and then Jennifer Salim Arrigo, and now David Legler. They've all been hugely supportive of this effort. So thank you, everybody. Let's get it rolling here. Oh, more thank yous. Yeah, sorry. Thank you to our advisory panel members for your support, your advice, your guidance, and your patience for the team members who really didn't know a lot about paleoclimate, maybe still judged not to have too much knowledge. Incrementally more than we had to start off with. Okay, so the outline here for this talk, I'll talk a little bit about the goals and deliverables of the LMR. I think we're on pace to deliver what we said we would. I'll also do a very brief DA refresher, and the world leader in ensemble data assimilation, Jeff Anderson, is in the room. So Jeff, I'm going to apologize in advance. The linear algebra is minimal. It's mainly pictures this time around. But if you have questions, take them to Jeff. All right, so I'll talk about our framework progress. We have something we're calling the version 3 release candidate, which I believe is what we're using in a hackathon on Wednesday. So that's like the latest of what we're using right now, and it continues to be developed. I'm going to talk quite a bit about the verification process for LMR and uncertainty quantification, which I think is the most important piece. And it's something that nobody's seen before except from a few members of the team. I'm going to talk about the influence of the proxies on these reconstructions. And the teaser there is it's going to matter how we model them with what we call the proxy system models. It's going to matter a lot. Okay, so our goals and deliverables. We're doing paleoclimate data simulations. This is a relatively novel way of doing paleoclimate reconstructions with the goal of getting gridded climate data fields. So we're trying to do the same thing that we can do for climate variability, climate dynamics, climate thermodynamics that we do with modern reanalysis products. We need multivariate gridded data products over long periods of time. So that's the goal. We want these dynamically consistent space-time fields, which really are lacking right now. And the goal is the last 1,000 years. Most everything we're doing is the last 2,000 years, but of course, as most of you know, the number of proxies, at least the annually resolved ones that we're working with, really starts to drop off pre-1,000 years ago. So the promised deliverables are 2-meter air temperature, 500 hectopascal heights, precipitable water, a few others, sea surface temperature, overturning circulation in the ocean. Since nobody can challenge us on that, it seems like we may as well just put it out there. Ocean heat content, much more robust, I would say. I think we have a lot more confidence in that one, and a lot of common climate indices. And we're constantly adding to this. Basically, anything that's output from an Earth system model, we can update with data assimilation. How much you believe it is another story. And that really relates to this comprehensive uncertainty quantification. That's the key for how much you should trust anything. And this is going to include errors from the proxies, the models, and how we model the proxies, these proxy system models. So with respect to Sam's statement before, whether we trust the models or the proxies, we don't trust anything, right? It's all wrong. We know that. That's the a priori assumption. Just a matter of how wrong it is, and that really is the key for providing the weights. And so we do this Monte Carlo approach. This is something that you really can't do in operational reanalyses. So the big government centers that do like ERA 40 or NNRP, they're not doing 10,000 or 100,000 reconstructions, varying all of these components, including the observations that participate in the reconstruction. That's something we can do, and that's something that you'll be able to do once we share the code publicly, which is coming up pretty soon. Okay, so here's the picture. There is, I guess, a little bit of linear algebra on here, but I won't highlight it. But the basic idea, is there a pointer, or is I just use my finger, I guess? Okay, so we've got the climate model states on the left, And we're mainly using those to constrain the spatial and intervariable relationships. So these encode our knowledge of the physics of the climate system, but we're not trusting them to get the year-to-year variability right. Then on the other side of the plot, we have the measurements, the proxy measurements, and that really is where the time information is coming from in most of what I'm going to show you. And then we need this map between these two. So a lot of climate field reconstructions do inverse modeling, where they take the climate states to be a function of the proxies, which is a bit of an odd association. I think the more natural association, is to go this way from left to right through these proxy system models. So we need models for the trees, corals, ice cores, or whatever else we happen to be using here. And this is where I think the future holds the most promise. We're going to be doing some pretty simple things. We have been doing pretty simple things with the LMR, and we've been sticking with it, in part because it's been working pretty well. And to do better than this, I see smiles from the people who know, it takes a lot of work. But that's definitely the path forward, to go to physical and chemically based models. And then how do we blend these things? We use the Kalman update equation, so it's basically a way to assign weight to the new information we get from the proxies. So we're going to have an estimate of what the proxies are from the climate states once we run them through the proxy system models. And if we have perfect agreement, then this innovation, the difference between what the proxies say and what the models say the proxies should say, is 0, and we just stick with the thing we started off with, which is our prior. When there's a difference, which there typically is, then we have to weight that through this weighting factor, the Kalman gain, and that depends critically on how much error we have in the proxies, this R, and how much error we have in the estimates of the proxies from the proxy system models. That is the key right there. So let me talk about these data relationships, how they run through the whole system. So typically, but not always, we have to calibrate our proxy system models. So we're going to be doing linear regression for most of what I'll show you here today. And so we have some period with calibration data, we have proxy data, and then we calibrate these PSMs. And even for physically or chemically based PSMs, there is often a step, but that's why I dashed this line. Sometimes they really are completely free of calibration, and that's the ultimate goal. Then into the data assimilation, we have an estimate from the climate model. That's our prior guess as to what the climate state is. As I mentioned just a moment ago, we have to run that through our proxy system model to get our estimate of the proxy, which we then compare with the proxy, and that difference gives us the innovation. The new thing about the climate system, the new information that we didn't know before, we then weight that against the prior, and we get the analysis. That's the reconstruction. Okay? And then we vary all of these things and do this tens of thousands of times to get at the uncertainty. So the latest activity I'm not going to talk too much about because there are other talks devoted entirely to these topics. So we've been using what's called offline data assimilation. So the predictive skill of climate models on these annual and longer timescales is very weak. The models are very expensive to run, so the cost-benefit analysis is not very compelling for doing this by cycling like we do in weather data assimilation. So we do an offline approach where we're basically just sampling randomly from the climate attractor of the model. So that's extremely cost-effective, and it's basically what you get when you go beyond the predictability horizon of the climate model. It doesn't cost anything. So our version 3 release candidate, we've changed our linear statistical proxy system models from being linear on annual mean temperature to being seasonally dependent and bivariate, so temperature and precipitation for things like tree ring width. And that's a paper in prep, and Robert's going to talk about that tomorrow. Andre will talk about this online stuff tomorrow as well. We're using the Pages 2K Phase 2 proxies that Julian and his consortium members just published recently, whereas in the paper we published last year, we used the version 1 data. Then there are tests of physical models that Sylvia D. and Nathan Steiger and others have been pushing us forward on. And then we have some work where it actually uses preliminary results from the LMR to show we can do climate dynamics. And I think the interesting thing through all of this is that we're not just inheriting what we get from the prior, what we get from the CESM in most cases. When we assimilate the proxies, we get a posterior that's very different and gives us dynamics that are different from what the model would say. And I think that's the most interesting part of this whole exercise. I don't want to dwell too much on this, just highlighting the difference between version 1 that we published on last year and this upcoming one. The biggest differences are these proxies, so an enriched proxy data set, the observation models, like I said, and the data simulation. There's a lot more whiz-bang there, but nothing that you probably care about too much until you start going into the hackathon and embracing that code for yourself. Okay, so for the uncertainty quantification, as some of you may remember, what we do is we withhold a quarter of the proxies for independent verification. We assimilate 75%, and then we do this many, many times. So every proxy gets to be assimilated and also gets to be independent. We vary our priors. Most of them are coming from last millennium simulations from 850 to 1850. We've played around some with reanalyses as well. Most of our ensembles are about 100 to 200 members. And we use an identical, once we draw, we close our eyes, stick our hands in the bag and pull out an ensemble, and we fix that for all years so that all of the temporal variability is coming from the proxies, not from the prior. Proxy system model calibration, we use the usual suspects. And then, like I said, we have this Monte Carlo approach to uncertainty. For verification, we've been doing a little more that's on here, but mostly what I'll show you is correlation, which is kind of a weak test, mainly just getting at timing. Coefficient of efficiency is a much stricter test, which deals with errors in bias and amplitude. And then spatial anomaly correlation is another relatively strict test on how well we're getting spatial patterns year in and year out, but I won't have time to show that to you today. Okay, this is a reminder where we were with version 1. So this is the LMR compared with 17 other reconstructions, not all of which are shown here except for the average over those 17. This was in the IPCC report. And for the most part, there's broad agreement on the millennial scale cooling, something that resembles medieval climate anomaly, the downward trend enhanced during what we call the Little Ice Age, to the crescendo here during the 19th century, and then the upswing during global warming. Comparisons correlating the LMR against these the 17 reconstruction mean, what we see is that basically those other reconstruction techniques seem to agree more with themselves than they do with LMR. So the LMR does seem to be bringing something new to the party in terms of reconstructions. We're participating in another group activity with pages to reconstruct the last 2,000 years using different methods and comparing the methods and their performance. This just shows for the 7 methods how they ranked with respect to independent verification data. So here's composite plus scale. The little symbols show you for these different verification measures, root mean square error correlation, relative error, CRPS, and interval scores, that it's pretty consistently performing around 5th. So it's number 5, 1 is good, 7 is worst. And then these bolder symbols show you kind of some aggregate summary averaging over all of these measures. And this is the LMR on the right. So this is a good place to be. Probably can't see the symbols there, but we're number 1 rank in almost all these things. The only one we're not is in the interval score at 95%. So the very tails of the distribution. It seems to be we have a little too much variance out there in the far tails, but if we have to make a mistake, I'm comfortable with that one. All right, so looking at Detrended global mean temperature, version 1 on the left, version 2 on the right. There's this extra thick green line on the right that's not on the left. That's the consensus average over all of these other reconstructions, not including the LMR. And that's my favorite measure for comparison against, because it kind of averages out the uncertainty in all of these reconstructions. And basically, there's not a dramatic difference between version 1 and this version 3 release candidate, but you see it in the CE. There's a consistent upward tick and a large upward tick. So these figures are all significant. So when we change that last digit, it really means something. We have to work hard to get every single one of these, and we're seeing in the Detrended CE over this 1880 to 2000 time interval a jump relative against the like GIFs from like 0.5 to 0.62. That's a fair bit of skill by taking the trend out. Spatial verification, again, version 1 on the top, version 3 on the bottom. We had this relatively poor performance where we had a lot of the proxies, a lot of the trees over the southwest US, near the ice edge and a little bit over Central Asia. The latest reconstructions have a lot more red, so things have gotten better. We've removed a lot of that red in the southwest US and also across northern Europe. Some places have gotten a little bit worse, but on average, the global average value has about doubled. So we've extracted a lot more information from the proxies. And, you know, people say, wow, what's going on here? Why are you so bad where the trees are? Well, you know, I've been hit over the head with this so many times. Let me just remind you that there is a reference here, and that is the other state-of-the-art reconstructions that use a data assimilation system as good as ours. They do it every 6 hours using instrumental data. And when we verify them against GISTEMP, this is the 20th Century Analysis, basically our big brother. And this is the ERA-20C from European Center. And this is the LMR again, both verified against GISTEMP. We can quibble about GISTEMP, but the point here is that if you worry about these little blue dots, it has to be relative to some reference, right? And I think we can agree we're doing better than the reference. Okay. How about verification against proxies? So red is good, blue is bad. This is correlation, and this is in the pre-calibration period, so pre-instrumental, so from 0 to 1879 CE. On top are the proxies we assimilated, so we take our reconstruction, we run it through our forward model, and we compare straight up with the proxy records. And then down bottom is the harder, more important test. These are the proxies that we didn't assimilate, right? So we didn't see these. We see how well we can reconstruct those records. And it seems like we can do a pretty reasonable job. Perhaps not as good as we can for the ones that we have assimilated, but it's still pretty good. Summarizing those in terms of distributions. Now we've got on the top row, this was the version 1. This is the version 3 release candidate, correlation on the left, CE on the right. And we see quite a big jump in the version 3 release candidate. And I think I'm going to hope to try and convince you that this is because we're using the seasonal proxy system models and we're treating the proxies more faithfully. The blue and the red show you the performance during the calibration period, 1880 to 2000 and pre-calibration. It's reassuring that those distributions overlap. That says that these proxy system models appear to be stable. If there's a big difference here, it would suggest that these are unstable calibrations, that the proxy system models are changing over time. Doesn't appear to be the case. We don't get as much of a jump for CE. For the proxies we didn't assimilate, and we see a little more of a shift there. So there's a hint, maybe there's a touch of overfitting during the calibration period, but it's not dramatic. Okay, just a little bit on how this has changed our understanding of things like the MCA and the Little Ice Age. From a global mean perspective, we and everybody who's participating with us in this Pages 2K comparison have essentially lost the signal of the MCA in the global mean. Okay, so with Pages 2K phase 2 data, it seems to have disappeared. But it's still there if we look regionally, but not as dramatically as it was. So here's our version 1. Here's our version 3 release candidate for the MCA relative to 1960 to 1990. And here's Manadal. Okay, so we looked quite a bit more like Manadal in version 1, except our warm center was shifted from Greenland to Scandinavia. Now that has cooled quite a bit. Little Ice Age is fairly similar. The difference, we see the biggest changes over the lower 48 of the US, over North America, and a bit over the North Atlantic. Still a fair bit of warming, though, at high latitudes. And I think we have some hints as to why this is the case, which is what I'm going to get into now, which is, am I doing okay on time? Okay, great. Thanks. Great. Okay. Thank you, Sam. So this is new work. It's still in a work in progress. It's only one way to get at the influence of proxies, but it's a standard one in the weather world. So let me just throw it out there and see what sticks. Get some feedback. So we're looking at the influence of proxies on these reconstructions in proxy space. That's different from looking, say, in the gridded space, which is also something we plan to do. The reason why we're doing this first is this is kind of a standard way to do this in the weather world. This is what's sometimes called the ECMWF method. It's how they measure observation impact in the operational system that the European Center uses. And I'm not going to give you the math, and I'm just going to tell you in words, and you're going to have to trust me for now, that we're going to get a large influence on a per proxy basis for spatially isolated proxies that have small error. Right? Those are the ones that are going to pop the most. And we're going to get a small per proxy influence when they're spatially dense, which they sometimes are for things like tree chronologies, and when they have large error, which is also the case for tree chronologies. Okay? So perhaps the most important message to take away here is that this is really going to highlight the importance of the prior. Not just how we model the proxies through the prior in these proxy system models, but the fact that the proxies communicate their influence to other locations through this covariance matrix that we get from the prior. That's going to turn out to be really important because it effectively reduces the influence of other proxies. All right, well, let's just jump right in here. In our version 1, so I'm going to show you a bunch of symbols where we have proxy records. They're color-coded by the type of proxy that they are, and the size of the symbol indicates how much influence they had. Bigger symbols, bigger influence. So the tropical corals were having a very large influence. There weren't very many of them, but I think the most valuable record we probably had, even though it was in the wrong place, was Palmyra. Phase 1 pages had the wrong latitude, but you know, it's only 6 degrees off the equator, so you know, what's 12 degrees of latitude among friends, right? That has been corrected. We see that the trees are having a fair bit of influence. Let me just go straight ahead to what this looks like in version 2 now with many more proxies. Palmyra in the right place. And a lot more of other sorts of proxies. So there's a lot more tree ring density information. The symbols have all gotten a little bit larger. We're still looking at annual mean temperature here. And if I summarize the total impact by proxies, I'm sorry if these fonts are really small, I don't have time to put them on here, but here's the tree ring width. So the total impact is dominated by ring width and coral delta 18O, right? And if we do this on a per proxy basis, so we divide by the number of proxies, then we're going to whack the trees because there are so many of them, right? So, you know, large numbers really help. They're really noisy, but we've got a lot of them, so the total signal they give us is the biggest. But on a per proxy basis, the corals are the ones that are most valuable. I thought you would appreciate that, Kim, but take your patience pills. It's not going to last long. Yeah, yeah, David. Apparently not, right? Here they are. So, yeah. Oh, if you sum them together. Yeah, it's getting close relative to the strontium calcium. All right, well, what if we go to, this is on a proxy basis. So again, I can't go into all the details here, but this is basically how many degrees of freedom can we get with this information. The trace, okay, yeah. Well, so this is the self-importance. So it's the diagonal part of that influence matrix. So they do sum from that perspective. So the trace of that matrix is the total influence, and so each individual element you can add them up and look at its fraction of the total that it accounts for. Okay. Fair enough. They still don't matter very much. All right, so here's what happens when we use the latest and greatest proxy system models. So I didn't rescale the symbols. I used the same scaling. So now we're using seasonal temperature and bivariate modeling for the ring width. And the symbols have all gotten bigger. We're getting more information from the proxies now. And some of these proxies have started to get really influential, right? So this is not a shock, right? Everyone tells me, well, of course, everyone knows MXD is a temperature, seasonally sensitive temperature proxy, right? Well, how much influence does it have, and how does it compare with others? You need to do this calculation to estimate that. Now, if we do this on a total influence basis, ring width really starts to stand out now. We're treating the trees with greater fidelity than we were with the annual mean temperature. And tree ring density is really standing out tall. This is total width. We haven't even normalized yet, so you know where this is going. But before I go to that, let me just say that in these degrees of freedom units, these mysterious units where bigger is better, the total influence of the proxies now, in terms of the number of degrees of freedom we can account for, is 70 when we go to the seasonal PSMs, where it was 22 with annual mean temperature, right? So we are wringing a lot more information, more than 3 times as much information out of the proxies by doing a better job with the proxy system modeling. However, the rest of that, so there were 538 proxies, the rest of the impact is coming from the prior. That is 87% of the influence at these locations is the prior. And it just got very quiet in the room. How does this compare with the European Center? Well, the European Center, they assimilate, what, 100 million observations roughly every 6 hours? And 85% of their analysis with those 100 million observations is coming from the prior. So this is a little bit hard to understand, but it's not just the prior. So we need the prior to estimate the proxies and to provide a weight, but they're also communicating in the information from proxies to other places. And if we can get those relationships well, that magnifies the influence of the proxies. That's another way to think about this. So now if we normalize on a per proxy basis, we get the big tree in the histogram is the tree ring density, right? It's this massive, massive influence relative to everything else. And even the ring width starts to stand up pretty much as the number 2 most important on a per proxy basis. So the upshot here with this first stab at this is that better PSMs are going to yield greater proxy impact. And I think this is the future, right? This is where we have to invest because this is where we can have the biggest impact. 87% is coming from the prior, spreading this influence around. Yeah, this is just a summary of what I just said. All right, so let me conclude. The Last Millennium Reanalysis is going to provide this new globally gridded data set. I feel like I'm a little surprised by the quality of this reconstruction. I was mentally setting the bar low. I don't know what the community felt where the bar was going to be. Ultimately, you get to decide how valuable this data set is going to be, and that's why we're so excited to have the hackathon, put the data and the code in people's hands, and see what they do with it. We're fusing proxies and models in an objective way. And I didn't get into this, but you should pay close attention to those other talks that I mentioned. The results, these reconstructions, differ very substantially from what we see in the Earth system models. And I think that's really important. And that is coming from the proxies, not from the models. We have a fair bit of skill when we measure against independent proxies and instrumental data. We're planning, we have not an exact release date, but sometime roughly mid-2018. I think we're on pace. The hardest part is probably going to be packaging up these netCDF files in a standard way and finding out how we're going to distribute them. There's a little bit of discussion / debate going on inside of NOAA. We want to be distributed just like the 20th century analysis with the same web-based tools for interactive work with the data. So you can contact your NOAA representatives and ask for that, because that will be helpful. Of course, it's constrained by resources. We're asking them to use resources to do that, but we think that will be the best way for people to work with this data. Anyway, we are also going to be the first reanalysis that I'm aware of that actually gives you the tool and not just the data. And you know, there are a lot of things that are very hard about this problem, about paleoclimate data assimilation. We can moan and groan about all the difficulties, but the fact of the matter is, it's a relatively small calculation. We could do things that you simply can't do with NNRP or ERA type reanalyses, like do it 100,000 times, or sample the errors in ways that they can't, or do it on your laptop, or give people the tool so that they can do it themselves. So that's the thing that I'm most excited about, is that we're going to make this publicly community-based tool. It's on GitHub right now. It'll be opened up to the world, and hopefully it will continue to evolve, because I think there's a pretty clear path forward here that we have a way to improve this. Better PSMs, I think, are the most important thing. We're going to inherit improvements that come through Earth system modeling improvements, and because we've figured out how to linearize these things and get the predictive signal. That's most important for us. That's what Andre is going to talk about tomorrow. That's only going to get better. And where we need to get a little better at handling multi-scale proxies. Nathan Steiger and others have sorted out how to do that, but to do it in an efficient operational way is still something that we need to sort out. Okay, hopefully you're jazzed up about LMR now, so I'll stop there and take questions.